Hi guys, so welcome back to another episode of our Route to Conquering Acid-Base Equilibria series. So picking up from where we left off previously, today our little Mario is going to move on to finding the pH of a buffer solution as well as understanding the fundamentals and concept of buffer solution. So in a nutshell, what is a buffer solution? Simply put, a buffer solution is a solution that is capable of resisting pH changes when a small amount of acid or base is added to it. So how does it achieve that? We'll find out how mathematically a buffer is able to resist pH changes later. But how is a buffer solution created? Essentially, there are two kinds of buffer solution. One is an acidic buffer, where it contains a large reservoir of unionized weak acid, so we call it HA, and similar concentration of its conjugate base, which is A-. So as long as you have around the same concentration of HA and A- in your solution, we can call it an acidic buffer. Likewise, for a basic buffer contains a large reservoir of unionized weak base, which is B, and its conjugate acid, which is BH+. So as long, now we see it in the next slide. So as long as your solution contains some similar concentration of HA and A-, or on the other hand, if your solution contains similar concentration of your base and your conjugate acid, we can call both of these solutions buffer solutions. Okay, so I think in this 1 minute or two, you can understand what is you can visualize how a buffer solution can exist, what the conditions needed. Now we need to know how to prepare a buffer solution, or how can you identify that a buffer solution is created properly. So just now, as I mentioned, the conditions or the end result of a buffer solution is when your solution contains similar concentrations of whether it's weak acid and its conjugate base, or weak base and its respective conjugate acid. That is when you can identify that yes, a buffer solution has been created. So there are two ways about going about preparing a buffer solution. Firstly, we can mix the weak acid or weak base with its salt. So what do I mean by that? So let's take a look at this diagram again. So now let's talk about the using weak acid first, acidic buffer. So suppose we start off with like a weak acid called HA. So in order to create a buffer solution, we will get its conjugate salt or prepare its conjugate salt. In this case, we call it Na, that means sodium, and the sodium will be cation, and the anion will be the conjugate base of your weak acid. So let's see what happens when they dissolve in water. So your salt, being a group 1 salt, it should be able to dissociate completely in water, while your HA, it will dissociate as a weak acid, it won't dissociate that much, but in this case, the degree of dissociation is even less. So let's take a look at why is that so. But before that, now you can see, has the conditions been met? Yes. See, as you can see, the conditions of similar concentration of your HA as well as your A-, the conjugate base, they both have similar concentration, and as such, we have already prepared a buffer solution. So you guys might have some questions with regards to why don't HA dissociate partially to give some traces of H+ ions, or on the other hand, why don't your conjugate base, being a strong conjugate base, undergo hydrolysis? So let me just simply use a few equilibria to explain why is the case here. So your HA, in the normal basis, when you put it in water, it will undergo a partial dissociation to give you your A- and your H3O+. On the other hand, as a strong conjugate base, it can undergo salt hydrolysis. So these two equations can technically happen under a normal basis. But now let's think about it. So let's look at the weak acids dissociation first. So this on a normal basis, when your solution is just like a pure water solution, dissolving your H+, there will be some traces of dissociation or partial dissociation. But in this case, since our solution already contained A minus in the first place, so if you can think about it, your A minus concentration is pretty high to begin with. Using the Chatter's principle, our our position equilibrium will be much shifted to the left, and this will help to actually suppress the dissociation of HA. Okay, I hope you can see it using your equilibria knowledge. So on the flip side, again, we look at the hydrolysis of your conjugate base. On a normal basis, without any HA to begin with, yes, there will be a degree of like soft hydrolysis will happen. However, in this case, now our solution contains large amount of HA. Likewise, the position of equilibrium will be much shifted to the left. Say for this guy here, much shifted to the left. So here, there will be very little. The soft hydrolysis is also suppressed here. That's why when you put two of these together in the buffer solution, there won't be much. While there will be still certain traces of like dispersion, minute amount of dissociation and hydrolysis. Overall, there won't be any more H plus remaining in this solution. Okay, so yeah, I think I went too long about that one. So the second method of actually preparing a buffer solution, in this case, it's called partial neutralization. So maybe in hindsight, now when you're doing a question on titration curve, right? What you realize is you have been actually, or the question has been always preparing buffer solution through partial neutralization. As such, there is a titration curve that can be created. So yeah, they will take a look at the titration curve question, and you see that actually what they've been doing is preparing a buffer solution through partial neutralization. So let's say we already have some weak acid, as I said in the titration curve. Let's say like initial pH, or like initially there is 25 cm³ of weak acid in the conical flask, and your NaOH came from the burette, is prepared in the burette. So while yes, if you do your equation, your HA plus NaOH, in order for full neutralization to take place, each of them should have, just let me a while I write everything out. This should be equal amount of moles, right? So if I have 1 mole of HA, it takes another 1 mole of NaOH to fully neutralize. But in this case, we do not want to do so because we are trying to prepare a buffer solution. So let's say now we have 4 HA to begin with. Let's say again 4 moles of HA. What if I put in 2 moles of NaOH? Let's see what will happen. I put in 2 moles of NaOH. Yes, again your NaOH dissociates fully to give you OH minus ions. So your weak acid, being a weak acid, and I mean as an acid and here as a base, there is some neutralization reaction that will happen. So as such, you will get your salt and water, but the other 2 moles of HA who don't get the chance to react with NaOH will just be sitting here in the beaker as well. So at the end of the day, again, how do we know that a buffer solution has been created? We can identify whether your weak acid and your conjugate base has relatively similar concentrations inside the solution. And using this diagram, yes, we can say so. There are equal moles or equal concentration of HA and A minus. As such, a buffer solution has been created. So I think I think I went a bit too long for this video, but hopefully now that you have 2 ways of preparing a buffer solution, now that you know that there are 2 different ways of preparing a buffer solution, hope that when you do MCQ questions regarding preparing buffer, or when you're doing a titration curve question, at least you know what you're doing. Yeah, so the next video will be calculating the pH of a buffer solution using new formulas that will be introduced in the next video. See ya!